right, next I'd like to look at another two-body problem, but in this one we'll also combine some of the aspects of what we've learned before about an inclined plane. And so again, we've got a coupled system here. Let's assume that the plane has an angle of 30 degrees to the horizontal. And in this case, let's make M1 equal to 50 kilograms and M2 equals 100 kilograms. And let's ask, if there's no friction, let's find the acceleration of the system. All right, so we already know that the mass is going to have a mg sine theta component of the weight pulling it down the incline. And so maybe the first thing to try to do here is to just get a basic idea of which way it's going to go, okay, before we actually define a positive direction to our coordinate system. And so what I would want to do then is I'd say, well, how much force is this? M2g pulling straight down. And let's compare that. M2g to M1g sine 30. Okay, because that's the component of the weight that is accelerating the mass down the incline. This is M1g, this is theta, which is 30 degrees, the angle of inclination of the plane. And so this component, which I'm just moving up so that it's acting through the mass, is the M1g sine 30 term. Okay, and so M2g then is going to be 100 kilograms times, rounding off again, g to 10, that'd be 10 meters per second squared, so that's 1,000 newtons. Whereas M1g sine 30 is going to be 50 kilograms times 10 meters per second squared times the sine of 30 is 1/2. Okay, so that's going to be 500 divided by 2 is 250. This is 1,000. So 1,000 newtons is greater, clearly, than 250 newtons. So that tells me that the hanging weight is going to dominate and it's going to pull M1 up the incline. So I'll define the positive direction for M1 as the positive x direction as being up the incline along the direction of the inclined plane. And then I can define the y direction to be perpendicular to the plane. Then over here, I can define the positive direction to be down for M2g. And then we can draw our vectors in. M2g, this is going to be a tension force. But I know the tension force must be less than M2g because I already know it's going to go this way. The forces are dominating this way, and that's going to pull M1 up the incline. So M1 is going to be accelerating up the incline. But that tension is going to have to be larger here than M1g sine 30. In order for it to accelerate this way, the sum of the forces has to give you a net force that's up the incline. Whereas here, this net force has to give you an acceleration downward. Okay, so you don't have to draw your vectors to scale like that, but it's a really good way to double check that you're doing things right. When you get answers later, you can look and make sure that your answers are reasonable. Okay, so now we also need, for M1, in general, we need the normal force. Okay, and so the normal force is going to be compensated for by M1g cosine 30. However, if there's no friction, we don't really need the normal force in order to calculate the acceleration up the incline. But nevertheless, I'm going to add friction to this problem in a little while. So let's just, because you're likely to see this with friction on, not always, but oftentimes you'll see a problem like this with friction on a quiz or an exam. So what I'm going to do then is say, well, okay, the sum of the y forces on M1 is going to be F normal, because this is the positive direction for y, minus M1g cosine 30 is equal to 0. So that gives me the normal force, and we've seen this before, is M1g cosine 30. Okay, so we'll just kind of save that for later because we'll need that when I add friction to this problem later. Okay, but for the moment, we can say the sum of the x forces acting on M1 is equal to MA. M1A. Okay, so what have we got? On M1, we've got the tension force this way, and M1g sine 30 that way. Okay, so we can call this, if we want, our equation 1. Okay, that deals with M1. Okay, now for M2, we can say, well, there's only one direction to worry about here, and that is the, where we're calling the positive y direction down. We can write this as M2g minus t equals M2a, because we know M2g is bigger than t, and we're calling the positive direction the direction of motion for both of them. That's why this is t minus M1g sine 30 equals M1a, and this is M2g, the bigger of the two, minus t equals the direction that's moving M2a. So that's our equation 2. So how do we solve these? Well, the first thing that we always want to do in a two-body problem, or in any problem where we have unknowns, is to make sure that we have the same number of equations as we have unknowns. And so here we see that, well, yeah, here's a tension, that's unknown, and here's an acceleration. So we've got A and T are our unknowns, but we have two equations with which to solve for them. And if we just add the equations together, let me just write them over here next to each other in the same basic form. T minus M1g sine 30 equals M1a, and M2g minus t equals M2a. And then we just add these equations together, and then the coupling tensions are always going to cancel if you've got it set up so that the positive direction is the direction of motion. As long as you've defined it that way, then you're in good shape. If you haven't defined it that way, for example here, if you've defined up as positive, then this acceleration is going to be negative, and that gets kind of confusing, and it adds a third unknown. Because then A2 and A1 are the negative of each other, which confuses even me. So I think this is a simpler way to do the problem. So let's go ahead then, we'll add the equations together. The tensions will cancel, so give me M2g minus M1g sine 30 equals M1a plus M2a. Then we'll factor our common factors of g on the left. That gives me M2 minus M1 sine 30 times g equals M1 plus M2 times a. Or that gives us a is equal to M2 minus M1 sine 30 divided by M1 plus M2 times g. Okay, so that's our expression without friction. And so now we can plug in numbers if we want to get a numerical result here. Might as well do that. We've gone this far. So we've got 100 kilograms minus 50 kilograms times, remember that the sign of 30 is 1/2. We use that one a lot in these examples. Okay, and then we'll divide that by m1 plus m2, so that's going to be 50 kilograms plus 100 kilograms, all times 10 meters per second squared. That's our acceleration, and this is times 1/2 here. That's to be written in there. 50 kilograms times 1/2. Okay, and so then that's going to be 100 minus 25 divided by 150, all times 10. So notice here again, I'm putting the units in here so that I can check my work. But in the last step, I don't really need to do that. And it just kind of gets in the way of me solving the problem for an answer. And so I'm leaving out the units and just crunching out the numbers. It's going to be 75 over 150 times 10, or that's just 1/2 times 10 is 5 meters per second squared. Okay, and so this system then is going to tend to accelerate at about half the acceleration due to gravity with no friction. So that's a typical kind of a solution, but the only problem with solving a problem like this way, is that it's, and this is often true in physics problems that we try to solve, is we make simplifications. And a simplification that is hard to justify in most cases is that there's no friction. And so let's look at a problem where there is friction. Okay, and so let's let's put a coefficient of kinetic friction onto this. And let's say that our friction coefficient now mu k is equal to 0. Well, let's make it 0.2. Now remember that the coefficient for kinetic friction is a pure number. And so 0.2 then is not all that much friction. We looked before at different examples of coefficients of friction, and so that could be like wood on wood. I think a 0.1 might be more like if you were skiing on the snow, the coefficient between the ski and the snow might be, say, 0.1. If you're talking about the fluid, the synovial fluid that makes your joints move smoothly, then you're talking about maybe 0.01. Unless, of course, you've got joint problems, and then it could go quite a bit higher than that if things start to lock up on you. But if things are working well, you're talking about a very small coefficient of friction, because you don't want a lot of friction when your joints are moving. And so nature has taken care of that for us. All right, so if we're going to find our acceleration, the first step in this problem with friction now is the same as before. We would compare M2 to M2G to M1G sine 30. And so we already know that it's going to tend to win. And so the system is going to tend to want to move this way, unless you already started moving the other way. Okay, but let's assume we give it a little tap, and we'll talk more about what static friction could do to this in a little while. Well, let's give it a little tap and make sure that it's moving up the incline. That's the way it's going to tend to move. So our coordinate system is the same as before. But what's going to be different here is that we're going to add the force of friction. And that force of friction is always going to resist the direction of motion for the object. Now M2 clearly is not touching anything, so it has no friction force. But M1 is always sliding and grinding across the surface, and so that's what we're referring to when we say that we have a friction coefficient of 0.2. It means the surface is rough enough to create that amount of friction force. We also know that Fk, the friction force, is equal to the coefficient of kinetic friction times the normal force. Now here's where our hard work before comes in handy, because the vertical equations aren't affected by adding in an extra friction force here. But so that means that the normal force still has the same solution as it did in our previous problem. Okay, so this then is going to be mu k times m1g cosine 30. Okay, because that's the component of mg that's perpendicular to the surface, and that's how much the surface has to push back on the mass to keep that mass supported against that component of the weight. But now we're going to have to adapt our equations here. We can't just say T minus m1g sine 30. That's not good enough anymore. The sum of our x forces for this problem now is going to be T minus Fk minus m1g sine 30 equals m1a. Okay. So we have this extra force, and that force is opposing the motion, and so that goes in there, and then we can plug in that the force of kinetic friction from this expression is mu k m1g cosine 30. So that gives me T minus mu k m1g cosine 30 for Fk minus m1g sine 30 equals m1a. Okay, so that's our new equation now. This is our new equation 1. Just like the old one, but with this extra negative friction term in there. And then the second equation, same as before, because although the friction force changes the solution to this equation, there are no direct forces on M2 to change that equation. It's just the solution to the equation that will change because of friction in the coupled mass. So we have M2g minus T equals M2a. So when we think about it then, this is just a natural extension of what we did before, but with an extra negative friction force in there. So now if I add the two equations together, the tensions once again cancel. It gives me M2g minus mu k m1g cosine 30 minus m1g sine 30 equals, and then on the right-hand side, we have m1 plus m2 times a. m1a plus m2a. So now, in the next step, I'm just going to factor out the g on the left side and the a on the right side, just like I did in the last example, just a little more algebra here. M2 minus mu k m1 cosine 30 minus m1 sine 30 all times g. Now some people will go in and they'll just plug in numbers right here and then try to solve the thing out. That's okay to do that, but the problem with doing it that way is that when you want to check your work, you'd have to go through every little calculation that you did. And so most people won't want to do that on a timed exam. So if you do it this way, you can work things down to one final step and then just check that one step and make sure the numbers went in, and you can check the algebra up to that point. So it gives you an opportunity then that you might not take otherwise to check your work. And so that's why I do it that way. If you don't feel comfortable with that, you don't have to, but it's suggested if you can make that work for you. So then here we solve this for the acceleration, and that'll be m2 minus mu k m1 cosine 30 minus m1 sine 30 divided by m1 plus m2 all times g. So plug this in. Now remember in the last example we got 5 meters per second squared. So here with an extra negative term in the numerator, I'm expecting that the acceleration will be less than 5. So that's a reasonable answer then. If it's more than 5, that's not a reasonable answer. Okay? And so here, this would be 100 kilograms minus mu k, so that's 0.2 times m1, which is, I'm sorry, yeah, this m2. m1 is 50 kilograms times the cosine of 30. That's root 3 over 2, or 0.866. It's the same thing as square root of 3 over 2 here. And minus m1, which is 50 kilograms, times the sine of 30 is 1/2, and that's divided by 100 kilograms plus 50 kilograms. It's all times g. Okay, so what we end up with then, well, we had the 100 minus the 25, so that's 75 minus here. Okay, so 0.2 times 50 is times 0.866. Let me just knock that off real quick. Okay, so that's going to be, let me just do that one more time. All right, that gives me 8.6 divided by 150, all times 10. Okay, so that'll be less than 1/2. This was 75 over 150 before, but it's 75 minus 8.6 over 150 now. And so that gives us 4.42 meters per second squared. Okay, so that then is less than 5 meters per second squared. It's not a lot less, but it's a fair amount less. And the reason it's not a lot less is that our coefficient of kinetic friction is a relatively small number. If this were a 0.5, then this number would start getting big. This would be more like, well, half of 50 is 25, so you times 0.866, 6. So that would be maybe 20. So it's 75 minus 20. So that would bring it down to maybe 4 meters per second squared. Okay, but that is not the solution. Now once we have this solution, we could then go back to our kinematics equations and ask a question like, if you start this thing moving, how long will it take to move, say, 5 meters up the incline? So now we have an acceleration. A is equal to 4.42 meters per second squared. And so now let's go back to a kinematics problem. Let's ask how long to move 5 meters up the incline. Let's assume that the mass starts from rest. Now this brings us back into kinematics because now we have the acceleration. It wasn't given to us. We had a fair amount of work that we had to do to get to that. But now that we have it, we can set ourselves again, and I hope that you're all doing this, set up a table of knowns and unknowns, and then identify which equation gives you the answer with the least amount of trouble. So we'll call this the x direction and say this is x equals 5. We'll set the initial velocity to 0. And so our knowns then are v naught, the acceleration, and the x displacement. The unknowns then are the time and the final velocity. And now clearly we haven't been asked for the final velocity, and so we can eliminate all of the equations involving this unknown because we don't care about it. And it's in all the equations except for one. So we'll pick the equation that doesn't have this unnecessary unknown in it. And so that leaves us with the third equation. That gives us x equals v0t plus 1/2 a t squared. This is the only one of our 4 kinematics constant acceleration equations that doesn't have a v final in it. Okay, and so the initial velocity is 0, and so the time then, t, is just the square root of 2x over a. And so for this problem, that would be the square root of 2 times 4.42 meters per second squared. I'm sorry, 2 times the height, or distance, x, so that's 5 meters, divided by the acceleration, which is 4.42 meters per second squared. Okay, so the time then is going to be 10 divided by 4.42 square root. And that gives us 1.5 seconds. Okay, so by solving for the acceleration, we can now start to predict what the motion of that particle will be and determine the important aspects of that motion at some future point.